Hi everyone. Let's go ahead and run through a full example of using the definition of the derivative function. You'll find that this work is really similar to what we were doing in the last section and a lot of the algebra we were doing at the very beginning of the quarter. But it does get a little bit messier because we'll have two variables in the mix now. And also, since we've been practicing this algebra so much, I decided to pick a fairly messy function. So hopefully this will be an interesting one still and not just feel too much like more of the same. Okay, so what's new is that instead of being asked to find m prime of 2 or m prime of -7 or something along those lines, we're just asked to find m prime of z. So this is the derivative of function m prime of z. And we've just built up the definition for how to do this in a more general way without picking the variable first. So we'll need the limit as h goes to 0 of m of z plus h minus m of z all over h. So again, really similar, but we're leaving the variable in now. So we will get, let's see, z plus h plugged into our function is 1 over 3 root z plus h. And then plain old z plugged into our function will give us exactly what we see up above. And that's our setup. So from here, we have to work on the simplify. We need to cancel out that lonely h from the denominator. To do that, we'll need to free up the h in the numerator, which in this problem is trapped not only in the bottom of a fraction, but also under a square root. So we're actually going to have to use both of our algebra tricks. And really, you can use them in either order, but what will make this look the most like it usually looks for us is if we clear the fractions first. So you could technically jump straight into a conjugate now. If you want to try that, go for that. I am going to say I would really like to clear a 3 root z from the denominator of the second fraction, and I would really like to clear a 3 root z plus h from the denominator of the first fraction, but I've already got the 3, so if you notice that, don't repeat it. If you do, it's not the end of the world. You'll just have an extra factor of 3 top and bottom. But if you spot it, you can actually make things just a little bit nicer for yourself. So we're just going to do top and bottom by 3 root z times root z plus h. And if you need it, you can always write those over 1 just to remember how things are lining up, mostly on the top here. So when we multiply the first fraction, we're going to get to cancel a 3 and a root z plus h, but we'll have a root z left over. Oh, let me get this started with the limit. H approaches 0. So we'll have a root z. And then when we distribute through to the second fraction, we'll get to cancel the 3 and the root z, but we'll have a root z plus h left over. And really where we start to get a big mess is in the denominator as we go. So this is h multiplied by 3 root z plus h. I'm going to rearrange just a little so it looks prettier to me. So I will make it a 3h, and then those two roots, you can combine them into a single root, just to remind you of some algebra rules. Roots split across multiplication or division, which means you can also combine them across multiplication or division, not addition, subtraction. Okay, I like this better. I don't have complex fractions anymore, but I do still have h in the numerator stuck under a square root. So now I'm going to use my conjugate, and because I carefully canceled the 3 out, I don't even have 3's floating around, which makes this even a little bit less messy. So we'll multiply top and bottom by root z times root z plus h. And in the bottom, again, it just keeps making a bigger and bigger mess. I think I'll write it down here because it's going to be kind of long. So I'm going to write the bottom first this time. 3h root z times z plus h. It's okay if we left those as separate roots. We'll sort it out at some point no matter what. And now we have times root z plus h. And on the top, we're going to FOIL it out. So the first two is root z times root z, which is just z. Again, if you're starting to get really good and see exactly how this is going to work out and you don't want to write all of the inside outside, that's fine with me, but I want to keep writing it to make sure everyone sees it. Now we have a plus root z times root z plus h. And again, if you want to, just to remind you that this is a property, when you're multiplying roots, you can combine that into a single root. Your inside is negative root z plus h times root z, so identical to the last one, but a minus out in front. And then your last is negative root z plus h times root z plus h. So the roots cancel, the negative does not, which means parentheses are really important here. So the limit as h approaches 0. Okay, and what happens? The roots drop out of the middle. And I can actually even do a little bit better. I get negative z minus h. So z minus z also drops out. Really, all I'm left with on the top of this fraction is a minus h, and then a fairly big mess in the denominator. Root z plus h. And then I get to cancel my h's, which means there's just a negative 1 left in the top. And now that that h is canceled, I can finally let h go to 0. It won't give me a 0 over 0 anymore, at least I hope not. So this is going to 0, and this is going to 0, which means, let's see if we can carefully collect it all. We have a negative 1 on top. I'm not writing the limit anymore because I finally took it. We have the 3 left in the bottom. And then this becomes the square root of z squared. And then this becomes the square root of z plus the square root of z, which is a 2 root z. Okay, so I think we can simplify a fair amount here. 1 is 2 times 3 is 6. And then I have z root z. There are other ways to write that, but square root of z squared should just be, technically it's the absolute value of z, but I'll take just plain old z here. I don't think we have a domain question we're really worried about. And then just the square root of z at the end. And that is my derivative function. So the derivative of m is negative 1 over 6. And if you want to, you could rewrite that as it's z times z to the 1/2. So z to the 3/2. So I don't have a huge preference there, but do try and simplify. So one of those nicer answers at the end would be great. Okay, that is the process for finding the derivative of a function. It's a little messier with the extra variables, but we did practice some of that in the review difference quotient stuff we were doing. And then from here, we can do all the same things that we were learning in the previous section. So the next part of this problem is, can we find m prime of 4 and then the equation to the tangent for the tangent line when z equals 4? So if we've done our work correctly, we just use the formula to find m prime of 4. 4 to the 3/2. So remember, 3/2 power is square root and then cube. The square root of 4 is 2. 2 cubed is 8. So we get negative 1 over 6 times 8, negative 1 over 48. Okay, and this should go down here. So instead of having to run through the entire limit definition for every single x value, we now have this formula and we could plug in as many x values as we want and get out as many slopes as we want. And then once we've got that slope, the tangent line process looks exactly the same. So we know the slope, I won't use m since that's the function name, is negative 1 over 48. And then to get my point, I need to find m of 4. What was m? M was 1 over 3 square root of z, so 1 over 3 root 4. Root 4 is 2, so that's 1/6. So my point is 4 1/6, and my equation will be y minus 1/6 equals my slope times x minus 4. And let's go ahead, you know what, it shouldn't actually be x. We were using z as our variable. So y I think is fine, but we'll keep that z. Okay, so two things here. One, I'm going to add the 1/6 to both sides. And 2, I'm going to distribute. So negative 1 over 48 times z. And this becomes a plus 48 divided by 4 is 12, so 1/12 plus 1/6. 1/6 is 2/12. So we get y equals -1/48z. What do we get? 3/12, which is 1/4. So that is my final answer for the equation for the tangent line. So a lot of the same things going on here, but just a little bit of a step out on how general we're being when we find our derivative. Thanks for watching.